What if I told you that astronomers have discovered over 5,000 planets orbiting other stars, and we can't see any of them directly? So how do we know they're there? Today we're diving deep into the fascinating science of exoplanet detection. Let's explore. Hey, space explorers. Welcome to D3 Discover Deep Dreams, and today we're answering a mind-bending question. How do we detect planets around other stars when they're too far away and too dim to see? From wobbling stars to cosmic eclipses, we're exploring the ingenious methods astronomers use to find alien worlds. If you love deep dives into space science, hit that subscribe button. Let's get started. Before we explore how we detect exoplanets, let's understand why it's so incredibly difficult. Imagine trying to see a firefly next to a massive searchlight from thousands of miles away. That's essentially what astronomers are up against. Planets don't produce their own light, they only reflect light from their parent stars. And stars are millions to billions of times brighter than the planets orbiting them. The nearest star system, Alpha Centauri, is about 4.4 light-years away. At that distance, even Jupiter-sized planets are impossibly faint and drown in the glare of their stars. Direct imaging is possible in rare cases, but most exoplanets are detected through indirect methods that reveal their presence through their effects on their stars. Think of it like being a detective. You can't always see the culprit, but you can see the evidence they leave behind. And that's exactly how we find exoplanets. The most successful exoplanet detection method is called the transit method, and it's responsible for finding thousands of planets. Here's how it works. When a planet passes in front of its star, from our point of view, it blocks a tiny amount of the star's light. We call this a transit, like a mini-eclipse. By measuring the star's brightness over time, we can detect these tiny dips. How tiny are we talking? For an Earth-sized planet passing in front of a Sun-like star, the brightness dip is only about 0.01%, 1 part in 10,000. It's like noticing when a single light bulb dims slightly in a stadium full of lights. That requires incredibly precise measurements. NASA's Kepler space telescope revolutionized exoplanet science using this method. Launched in 2009, Kepler stared at a single patch of sky containing about 150,000 stars, monitoring their brightness continuously. By the end of its mission, Kepler had discovered over 2,700 confirmed exoplanets. The transit method tells us several things. First, how big the planet is. Larger planets block more light. Second, how long it takes to orbit. We measure the time between transits. And third, the planet's distance from its star, using Kepler's laws of planetary motion. But there's a catch. The planet's orbit must be aligned so it passes directly between us and its star. Most planetary systems aren't aligned this way, so we miss most planets using this method. We only see the ones that happen to be in the right orientation. The second major detection method is the radial velocity method, also called the wobble method, and it was actually the first method to successfully detect an exoplanet. Here's the clever physics. Planets don't actually orbit their stars. Both the planet and star orbit their common center of mass. For massive planets or those close to their stars, this causes the star to wobble noticeably. As the star wobbles toward and away from Earth, its light shifts slightly in color due to the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it moves away. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, it shifts toward red. By measuring these tiny color shifts over time, astronomers can detect the star's wobble and infer the presence of a planet. In 1995, astronomers Michel Mayor and Didier Queloz used this method to discover 51 Pegasi b, the first confirmed exoplanet orbiting a sun-like star. They won the Nobel Prize in Physics in 2019 for this groundbreaking discovery. The radial velocity method tells us different information than the transit method. We can determine the planet's minimum mass. Bigger planets cause bigger wobbles. We learn its orbital period, how long it takes to complete one orbit, and we can calculate its orbital distance from the star, the limitation. This method works best for massive planets close to their stars because they cause the biggest wobbles. Small, Earth-like planets in distant orbits cause wobbles so tiny they're extremely hard to detect with current technology. While most exoplanets are found indirectly, a few hundred have been actually photographed through direct imaging. This is the ultimate goal, actually seeing the planet itself. But remember that firefly next to a searchlight problem? To directly image an exoplanet, astronomers use special instruments called coronagraphs that block the star's light, kind of like holding your hand up to block the sun and see the sky around it. Direct imaging works best for planets that are young and therefore still glowing with heat from formation, massive, Jupiter-sized or larger, and far from their stars. These conditions make the planet bright enough and separated enough from its star to be photographed. Recent advances in adaptive optics, technology that corrects for atmospheric distortion in real time, have made direct imaging much more effective. Ground-based telescopes like the Very Large Telescope in Chile and the Gemini Observatory have captured stunning images of exoplanets. What's exciting about direct imaging? We can analyze the planet's light directly and learn about its atmosphere, temperature, and composition. We can literally see what colors the planet is. Beyond the big three, astronomers use several other clever techniques. Gravitational microlensing occurs when a foreground star passes in front of a background star. The foreground star's gravity acts like a lens, magnifying the background star's light. If the foreground star has a planet, that planet creates an additional spike in brightness. This method can find planets at great distances from Earth, including free-floating rogue planets that don't orbit any star. Astrometry measures the precise position of a star over time. If it has planets, the star will wobble not just toward and away from us, but also side to side across the sky. This method is extremely precise, and the upcoming Gaia Space Telescope is expected to find many planets this way. Timing variations look for changes in the regular timing of events. For example, pulsars emit radio pulses with clockwork precision. If a pulsar has planets, their gravity slightly changes when the pulses arrive at Earth. The first exoplanets ever discovered were found around a pulsar in 1992 using this method. Different detection methods reveal different properties of exoplanets, and combining methods gives us the complete picture. Transit method gives us planet size, orbital period, orbital distance, and sometimes atmospheric composition when we analyze starlight passing through the planet's atmosphere. Radial velocity gives us planet mass, orbital period, orbital distance, and orbital shape, how circular or elliptical. When we combine transit and radial velocity data, we can calculate a planet's density. Is it a rocky world like Earth, or a gas giant like Jupiter? This is crucial for understanding what the planet is made of. Direct imaging gives us actual photographs, atmospheric composition, temperature and color. We can literally see what the planet looks like. Together, these methods have revealed that planetary systems are incredibly diverse. We found hot Jupiters orbiting closer to their stars than Mercury is to our Sun, super-Earths larger than Earth but smaller than Neptune, and even Earth-sized planets in the habitable zones of their stars where liquid water could exist. The future of exoplanet detection is incredibly exciting. The James Webb Space Telescope is already analyzing exoplanet atmospheres in unprecedented detail, searching for biosignatures, gases that might indicate life. Future missions like Plato, planetary transits and oscillations of stars, will find Earth-sized planets in habitable zones around sun-like stars. Ground-based extremely large telescopes with mirrors 30 to 40 meters across will directly image Earth-like planets and study their atmospheres. And perhaps most exciting, the Habitable Worlds Observatory, currently in early planning, will be specifically designed to directly image and characterize potentially habitable planets. Within the next couple decades, we might find the first confirmed signs of life beyond Earth. We're living in the golden age of exoplanet discovery. From wobbling stars to cosmic eclipses, astronomers have developed ingenious methods to detect planets around other stars. Each technique reveals different secrets about these alien worlds, and together they're painting a picture of a universe filled with diverse planetary systems. We've gone from knowing only about planets in our solar system to discovering over 5,000 exoplanets in just 30 years. And this is just the beginning. What fascinates you most about exoplanet detection? Drop your thoughts in the comments. If you enjoyed this deep dive, give it a thumbs up, subscribe to D3 Discover Deep Dreams for more Saturday Space Explainers, and hit that notification bell. Until next time, Space Explorers, as always, keep looking up.